Hey everyone, this is John. In today's recitation, well, this is basically the last recitation of the semester, we'll be talking about non-homogeneous problems. So the first example I'm going to cover is Poisson's equation, and then the second example I'm going to cover is Eigenfunction expansion question. So the first 15-20 minutes should be about Poisson, and the last however long it is going to be is eigenfunction expansion. Just a quick note in advance, eigenfunction expansion questions are really, really annoying, but once you get the technique down, they're not the worst thing in the world to solve, but more often than not, I've seen eigenfunction expansion problems come up very frequently in the past few finals. For example, my final last year, I had one. The final for the class that I was TAing, I had one. And then for the class when I was taking it, I also had an eigenfunction expansion question. So they're very common, so I wouldn't be surprised if they came up on the final. So let's get started on this Poisson equation problem. So we're told to solve Poisson's equation inside a unit disk, yada yada yada, with the boundary condition u1 theta is equal to 5 cosine 2 theta. So as per usual, the first step is to draw the shape, which I've done here. And since we have Poisson's equation, we can't exactly solve this explicitly using separation of variables immediately. So the technique to actually solving this problem is what I like to call splitting the shape. And you may remember this from cylinder problems, for example, or original square problems, where we're basically trying to put, that's a really bad circle. We're trying to make at least one of the sides homogeneous and then make the other one non-homogeneous. So what I'm going to do is I'm going to set W equal to R squared. So I'm going to keep the PDEU as non-homogeneous, but I'm going to make the boundary condition of W homogeneous. Theta is equal to 0 plus another circle solution. V is equal to 0. So now we're solving Laplacian V is equal to 0, but V of 1 theta is going to be equal to 5 cosine 2 theta. So notice what I've done here. I basically decompose U into a linear combination of W and V, where W and V both are equations that we can solve using techniques that we know right now. In addition, W and V are much easier to solve than U on its own. So the claim that I'm basically trying to say is that U is a solution. So let's write it again. U is a linear combination of W plus V. So presuming I can solve for W plus V, for W and V, I can then take the sum of the two, and then I have a solution to my original problem U. So that's pretty nice. That's a nice way to go. Okay. So let's continue chugging along with this. So let's start off by solving the one that we actually know how to do. That's pretty clear, hopefully, and that's actually going to be V. Maybe I'll put V on the left-hand side because that's what we're doing first. So notice that V is Laplacian squared. V is equal to 0, and also the boundary of V, 1 theta, is equal to 5 cosine 2 theta. So we know how to solve this problem, actually. This is just a Laplacian problem with a non-homogeneous boundary condition. And the standard approach to do this is let's first define V as a product solution of f of r times g of theta, and then let's separate out the variables. So, and noticing on the top right hand corner the Laplacian for U or V, I can just click the Laplacian operator. I can move all the f terms to the left hand side now. So 1 over f r ddr, so I'm multiplying both sides with r squared as well. R df dr is equal to negative 1 over g d squared dg d theta squared. And this is equal to a separation constant mu, because on the right-hand side of this equation, we have periodicity conditions. Okay, so now let's solve the individual differential equations, because that was a pretty easy separation. So g of theta, in solving for this, is going to lead us to find, so this is from our table, and these are periodicity conditions. So g of theta is just going to be equal to c1 sine m theta plus c2 cosine m theta, where mu is equal to m squared for m equals 0, 1 to infinity. Right, so that's what's nice and easy. Now, the f term should seem somewhat familiar to you guys. Don't look at it immediately and think that it's going to be Bessel's differential equation, because that's just not simply going to be the case all the time. So the approach when you see these sort of Bessel-like diffie q's is to always expand it out and see if it's actually Bessel's differential equation. However, since we also have to account for the cases where when mu is equal to 0, let's be a little bit careful and first case for mu greater than 0. So when mu is greater than 0, I'm going to take this differential equation up here and then equate it to a non-zero mu. And then I'm multiply both sides by f, and then I'm going to expand the differential. So in expanding the differential, I should end up with r squared f double prime plus r f prime minus mu f equals 0. Remember that mu is equal to m squared, so I can just plug the value quickly in. And what you guys should be noticing right now is that this is clearly not Bessel's Diffie-Q. Bessel's Diffie-Q would have a r squared term right here as well. But this is Cauchy-Euler, and we know how to solve Cauchy-Euler because we've seen this problem so many times before. So in solving Cauchy-Euler problems, this currently gives us a solution of f of r is equal to c3 r raised to the m plus c4 r raised to the negative m. And now we have to essentially apply the boundary conditions that were given to try and eliminate one of the terms. So something I didn't explicitly mention, but hopefully you guys have caught on by now, is that since we're trying to solve the Poisson equation in a unit disk, we also have to account for the singularity condition at the center of the circle. Right, so the singularity condition, quickly repeating for the u case, is that the limit of u of r theta as r approaches 0 has to be less than infinity. So this is the boundedness condition. Hopefully that sounds familiar. Because the center of a circle in polar coordinates has a singularity. So this condition must also hold true for the f of r function. So taking the limit of f of r as r approaches 0 tells us that this must be less than infinity, and then for order for that to be true, we have to set c4 equal to 0, because the r raised to the negative n term starts to explode as r approaches 0. So therefore, since c4 is now equal to 0, we force it to be equal to 0. F of r is just going to be equal to c3 r to the m. And this is for the case when mu is greater than 0. So let's be careful now and make sure that for mu equal to 0, there's nothing really spicy that comes up. So for mu equal to 0, we have a slightly different differential equation. Not really, but hopefully you get what I'm saying. So let's take everything here, and set this equal to 0. So now let's get rid of the f terms and the r term on the outside, because we can just cancel those out to 0. And then let's take the integral of both sides. So yeah, integral, this is really ugly integral, but that's okay. Integral with respect to r, such that we get rid of the differential operator on the left-hand side of the equation. And then we're left with c1 on the right-hand side. Actually, let's call this c5, I think, because we haven't used c5 yet. Okay, c5. Okay, so now we're going to divide both sides by r. And then take the integral again, such that we're left with f of r is equal to natural log of r times c5 plus some arbitrary constant c6 again. Okay, so now let's apply the boundedness condition again. And in applying boundedness, and taking the limit as r approaches 0, we notice that the natural log term explodes as r approaches 0, because it's undefined at r equals 0. So therefore, c5 must be equal to 0. And then therefore, f of r is going to be equal to some constant. Let's make that a better 6. c6 for mu equals 0. All right, so why is all this like math useful? Now we can put everything into a general solution for v. So in v, remember that, so gensol, v is a composition of f dot g. So therefore, we can put everything into a summation now. We're able to put everything into one summation, starting from m equals 0, because for the m equals 0 case, all the terms can be summed up in one summation. This is definitely not the case for every single problem out there. For example, for damp wave equation problems, for the lambda equals 0 case, we have an explicitly linear function for m equals 0, or for the lambda equals 0 case there. So we cannot put it inside the summation, because the summation cannot sum everything up essentially for every single index. But in this problem, we're able to do that, and hopefully that sort of relation has made sense to you since the start of 241, hopefully. So then we have an arbitrary constant a(m), and then we have r raised to the m, and then we have sine m theta plus bm, different arbitrary coefficient r raised to the m times cosine m theta. Great. So now let's apply the general solution to solve for the coefficients. So v of 1 theta, let me just check the boundary condition real quick, is equal to 5 cosine 2 theta. So that means that all the sign-dependent terms on the right-hand side of the equation have to go to 0 because they don't matter anymore, because there's no dependency on that in the boundary condition, but we care about the m terms. And noticing the idea of like coefficient matching, it should be R1, so this is basically just 1. In coefficient matching, we notice that m has to be equal to 2. So therefore, b sub 2 is going to be equal to 5 for the case where m is equal to 2. So then our final answer for v sub r theta is going to be v r theta is equal to 5 r raised to the 2 times cosine 2 theta. And this r term comes from the simple general solution. So just look here and then match it up, essentially. So that's our general solution for v, our final answer for v. So now we have to go back up and solve for w now. So w seems a little bit nasty, but it's actually not that bad once you realize like what it actually is. So the convenient thing about w, right? Nabla squared w is equal to r squared, and then the boundary condition w, the outer side is equal to 0. So the nice thing about w is that it's actually a circularly symmetric problem. So this means it has no dependence on theta. And the nice thing about not having dependence on theta is we're essentially able to drop all the theta dependency terms inside the Laplacian. And if you need a review on this, I would look at the professor's notes or section 7.7.9 in textbook. So circularly symmetric problems is a very important idea that comes up in problems down the road. So the nice thing about circularly symmetric problems is that our relationship for the Laplacian simply becomes r, 1 over r, ddr, r dw dr is equal to r squared. Cool. So now let's multiply both sides by r, d dr, r dw dr equals r cubed. Take the integral of both sides now, such that we're left with r dw dr is equal to r to the 4th divided by 4 plus c1, I believe. Yes. Oh wait, let's not call it c1 because we've already used c1 like so many times now. Let's call this c7 because I don't think we've used that yet. Let's quickly double check. No, we have not. C7. Okay. So divide both sides by r again. dw dr is equal to r cubed, r plus c7 over r. Integral again. A lot of integrals here. So now we're left with w as only a function of r is equal to r to the 4th, 16, plus natural log r c7 plus another arbitrary constant c8. So now remember that we have various boundary conditions that we can use to actually solve for the value of these coefficients, right? So the first boundary condition, which is the obvious one, is w1 theta is equal to 0. So therefore, w at 1 must be equal to 0, and then applying this boundary condition, we find that c8 must be, let's apply 1 across, so let's be very careful here, 1 over 16 plus natural log of 1, so I almost made a very dumb mistake while doing this, so let's be very careful. So the natural log of 1 is equal to 0, so this tells us that c8 is equal to negative 1 over 16. Great. Now we have to deal with the c7 constant, and the way to do this is also to apply the boundedness condition here. So the limit of wr as r approaches 0 tells us that c7 must be equal to 0. Must be less than infinity, and therefore this tells us that c7 must be equal to 0. And the reason for this is because it's attached to the natural log term. As a natural log term approaches 0, it explodes arbitrarily to infinity. So we must take care of that term in order to satisfy the boundedness condition. Great. So this means that w of r is equal to r to the 4th, 16, minus 1 over 16. And does this mean we're done? Yeah, we're done. That's all we can find. Then that's literally our solution for this problem, for W bar specifically. Great. So now we found V and we found W. Remember that our original goal was to find U, and we defined U to be a linear combination of W plus V. So therefore, our final answer to this problem is U r theta is equal to r to the 4th 16 minus 1 over 16. So this corresponds to W plus the V term. So 5r squared cosine 2 theta. And that's our final solution to this problem. So notice that this extra term right here, which I'm quickly going to circle in orange, basically comes from the non-homogeneity of the problem. Specifically, the Poisson equation portion of the problem. Whereas the other portion of the problem could be explicitly solved if this was just a standard Laplacian problem without any non-homogeneity in the PDE itself. Okay, so hopefully that problem made sense, and if it doesn't, I would highly recommend you guys scroll back and rewatch the previous portion of this video. Sorry, the earlier portion of this video, maybe review it more slowly, but hopefully the sort of technique of how I split the problem up into its various pieces and then solved it out makes sense. Great. On to the eigenfunction expansion question now. So I'm going to be honest, eigenfunction expansion problems are probably the most tedious and annoying portion of Math-241, but since they come up so frequently, it's so important to be able to do these problems because they're just really annoying, and you probably just don't want to lose points on these problems since they're most likely to come up on your final. I haven't seen it yet, so I don't really know, but from past Math-241s, they have come up too frequently to not take a look into. Okay, so just a quick overview of what this problem is asking for. So it's asking us to solve a non-homogeneous PDE with homogeneous boundary conditions. So if you've taken Math-240 and you've seen like Ivan Lee's videos, like he usually identifies a PDE first. So that's what I'm going to do now. So step 0 is to identify the type of problem we're dealing with. So we're dealing with a partial differential equation, a non-homogeneous partial differential equation with homogeneous boundary conditions. So once you have identified the type of PDE, you should be able to identify the technique to solve it. So the most appropriate way to solve this problem is using eigenfunction expansion. So a brief overview of eigenfunction expansion, because I'm pretty sure Professor Garcia Juarez has covered the theory behind it much more extensively than I'm going to. I'm going to cover more of like a technical application of it. But eigenfunction is a technique that arises as a result of Sturm-Liouville theory, and essentially involves expanding an unknown solution in a series of eigenfunctions of related homogeneous problems. So right here where I'm basically put the expansion, u of xt is equal to an infinite summation of a sub nt times phi nx, is a direct consequence of the completeness property of Sturm-Liouville problems. And the completeness property, if you remember, is essentially the ability to write any initial condition, any initial condition in terms of a Fourier series. So in original problems that we've seen before, so I'm going to go on a quick tangent and I'll erase this after. U of xt is equal to sum a sub n of phi of x. Notice that a sub n here is a constant. And the reason why it's a constant is because we're able to write the initial condition in terms of phi of x essentially. So like for example, sine of x, cosine of x, or j sub m of r, or whatever. However, since these problems are non-homogeneous, right? The non-homogeneity of the problem is basically forced into the coefficient. So instead of a constant coefficient in these non-homogeneous problems, we're actually going to make these coefficients non-constant. So they're going to be functions in themselves. So just to reiterate myself, the non-homogeneity of the problem is being forced into the coefficient, a sub n of t. So this thing right here, right? So that's where the non-homogeneity of the problem is going. So the technique to solve these problems is really annoying. So let's start off by deciding on the appropriate expansion. So we're going to essentially solve the related homogeneous problem first. So notice that we're given homogeneous boundary conditions in the x direction. So we know that we have Dirichlet boundary conditions in x. So Dirichlet BCs in x. So u0 t equals u, I think it's 1. Yeah, 1. 1t is equal to 0. So therefore, we can solve the related homogeneous problem. So phi double prime plus phi lambda phi is equal to 0. And then in solving for this eigenfunction problem, this eigenvalue problem, we find that phi sub n of x is equal to c1 sine n pi n pi x, where lambda is just equal to n pi squared, for n is equal to 0, 1, 2, 3. So this is our homogeneous problem, right? So if we did not have a dependency on this non-homogeneous term, we would be able to separate out variables, and we would solve this as a standard heat equation problem, essentially. And this is our eigenfunction for phi. So obviously, the professor is going to cover this more in the terms of theory, but TLDR, we're basically trying to put the non-homogeneity of the problem into the coefficient a sub n of t. So therefore, we're going to take the eigenfunction, so the homogeneous case eigenfunction phi, and then expand out the solution in terms of this homogeneous problem, and then the non-homogeneous, like the coefficient that contains the data of the non-homogeneity of the problem. Right. So hopefully just follow along with this technique for now. It's obviously very new and it's very weird, but hopefully it makes sense after the end of this video. So the first step I'm going to take in solving this problem is I'm going to solve for, let's write this out explicitly, solve for a sub n times at t0, so at time equals 0. Remember that a sub n is a function of time. Okay, so we're given an initial condition, so this is just given the problem that u of x0 is equal to 2. And then, so now in solving for a sub n0, u x0, so we have the expanded eigenfunction of the form n equals 1 to infinity of a sub n0 of sine n pi x equals 2. So this is the eigenfunction thing I was talking about earlier. So for the homogeneous case, so that's what we're gonna expand our solution over the homogeneous case here. And then we can use orthogonality now. So the thing to note here is that since we're evaluating a sub n at time equals 0, a sub n0 is now a constant. Is now a constant, right? So when you evaluate a function at a specific time point, it becomes a constant. So we're able to like treat it as a constant and pull it out and ignore it when we're trying to solve for orthogonality. So in applying orthogonality ideas, right? So treat this a sub n0 as maybe like a sub n right now, because it's just a constant, right? We know how to solve for constants when we're doing orthogonality. So it's just 0 to 1 of 2 times sine n pi x dx over 0 to 1 sine squared n pi x dx, right? So all I'm doing right now is solving for the coefficient a sub n, right? Don't overthink this. This function a sub n can be a sub n of time, can be a little bit tricky, but right now this is probably just solving for time equals 0 case. So then we want to explicitly evaluate this relationship right now because it's going to help us down the road. You can just put this into a calculator and you'll end up with 4 negative 1 n minus 4 over pi n. And then this basically tells us that for odd n, our coefficient becomes a sub pi n. But for even n, this is just equal to 0. So this is some useful information to keep down the road when we're solving out the problem. So just keep this in the back of your mind while we're doing this. So now step 2 is to solve for a of nt. A sub nt. And this is a much long and winded process than initially meets the eye. So just hopefully follow along and we'll get through it together. So our goal is to plug the definition of our expanded eigenfunction. So plug u of xt equals n equals 1 to infinity of a sub nt sine n pi x back into the original PDE. Because the reason for this, right, is that if this function was supposed to, if this function, our function definition, is actually a solution to the PDE, then we would plug it back into the original PDE and then solve for a sub n of t. Then therefore that a sub n of t must be the sort of correction factor needed to solve the problem, essentially. Hopefully my terminology is making sense. So I'm going to quickly copy and paste the eigenfunction, the PD down here, so that we can reference it while we're solving. So the PD is this thing we did over here. So therefore, we need to find u sub t, so the time derivative. And taking the time derivative, so we have d sub a of nt dt of sine n pi x. And then we're going to take the position derivative, so the second position derivative, which is equal to negative, right? So second derivative sine is going to be negative, a sub n of t times n pi squared of sine n pi x. Yeah, okay. So now, looking at the definition of the PD, the PD that we were given above, ut is equal to uxx plus the non-homogeneous term, t sine 3 pi x. If we put that in, we should end up, so I'm just going to copy and paste this down here, like how we've been solving. So u sub t is equal to second derivative plus non-homogeneous term. Great. So now let's move the terms around, and hopefully you guys will see why I'm moving these terms around in just a moment. So since these sums are over the same sum, so we're assuming constant differentiability over a series. Move this here, plus everything in the sum over here, summation, and this is all equal to the non-homogeneous term left over. So now let's factor out the sign, because both terms have this sign dependence here. So now we have d sub n of t, so this derivative, plus a sub n t times n pi squared times sine n pi x equals non-homogeneous term once again. Okay, so just looking at this, right, it may not be completely obvious, but hopefully it will be obvious after I make the substitution. So I'm going to call this term inside the brackets, let's call this b sub n. So now b sub n, infinite series of b sub n times sine n pi x, is equal to some non-homogeneous term. What does this look like? This is literally a Fourier series, right? This is quite literally a Fourier series. And what do we do with Fourier series when we have a non-homogeneous condition? We will solve for the coefficient b sub n, right? So in solving for b sub n, all we need to do is apply orthogonality theory, right? So we're going to multiply both sides by sine m pi x over m pi x, and then take the terms that go to 0, right? So general solution for this problem is literally this, right? So it's going to be on the denominator 0 to 1 sine squared n pi x dx, and then on the top we have 0 to 1 sine n pi x times, actually let's put this over here. So we have the non-homogeneous term over here, negative pi squared t times sine 3 pi x times sine n pi x here. Okay, but notice that our integral is only with respect to x, so therefore we can factor out the stupid constant. For those of you who have taken Physics 280, you'll know what I'm taking these quotes from. But yeah, so now this is literally just a Fourier series, right? So we are able to solve for these coefficients explicitly. So the nice thing to know, right, is for what we know that for when n is equal to m, we have a non-zero solution, but when for n is not equal to m, we are 0. So looking at this relationship right here, for n is equal to m, so for when n is equal to 3, the top and the bottom are exactly equivalent to each other. So therefore the only surviving term for b3 is equal to e negative pi squared t. But then for all other n's, for n does not equal 3, b sub n is going to be equal to 0. Now, although it seems like we only need to continue going about with B3, we need to be very careful about the Bn equals 0 case. Because remember that Bn is equal to a differential equation. So just keep this in mind when we're going down here, right? We're not done yet because we need to solve for the various Bn's. So it's 2b is solved for Bn's. Yeah, this is really annoying. I'm sorry. So it's Bn's, right? So this is our differential equation Bn. Remember that we defined this to be Bn, right? So Bn is going to be either equal to, for B3, equal to e negative pi squared t, or Bn is equal to 0 for n does not equal 3. So then we're going to have two differential equations, two first-order diff EQs that we need to solve now, which is nice and fun, right? So let's first take a look at the n equals 0, n equals 3 case, sorry, because that'll generate solutions that are necessarily not zero, sorry. So in solving this diff EQ, we have this relationship, this explicit relationship, d sub nt dt is equal to a sub nt n pi squared is equal to e raised to the negative pi squared t. So this is an ODE now, right? So this is like throwback to MATH-241. This equals ODE, first order non-homogeneous problem. So yeah, I usually just use a formula to solve first order non-homogeneous problems because I'm lazy, but up to you if you want to solve it explicitly and do integrals, but I'm just going to use this formula. So a sub 3 t, so this is for n equals 3, is equal to 1 over integrating factor. So so remember, sorry, I should probably justify this. So we're looking explicitly for the 3 case, so we have to plug this in. So just for notation's case, so 3 pi squared is equal to, yeah, okay, now we're good. So you can find this formula online, but actually maybe I'll just write, yeah, okay, so you have to solve for this differential equation. I use a formula, but once you solve out this diff EQ for a sub 3t, what you should end up with is e raised to the e pi squared t over 8 pi squared e 9 pi squared t plus some arbitrary constant over e 9 pi squared t. So that's a sub 3. So remember how we solved for the time equals 0 problem earlier? Now we can use this to solve for the arbitrary coefficient. Let's call this C1. So at time equals 0, we know that for n odd, right? So let's quickly go back up. For n odd, A3, oh, where is it? Oh, God. Oh, it's here. Okay. For n odd, we're equal to 8 over pi n, but for even n, we're equal to 0. So that's for the a sub n0 time coefficient, right? So since n is equal to an odd number, we know that we're going to be equal to 8 over 3 pi, and then we can plug in time equals 0 across for the general solution for a sub 3t. And then if we just quickly plug in time equals 0, we find that 1 over 8 pi squared plus C1. And then this tells us that C1 is equal to 64 pi minus 3 over 24 pi squared. So this is just like algebra, but yeah. So then at the end of all this garbage, right, a sub 3 of t is equal to this term plus the C1 term, where C1 is equal to the thing we just solved there. Right? Yeah, so if we were to expand this out continuously and then do some more algebra, what we would find is that we have 1 over 8 pi squared e raised to the pi squared t plus 24 pi squared over 64 pi minus 3 e 9 pi squared t. Great. So this is our general solution for, well, this is our solution now for a sub 3t. the thing is, we're not done yet, okay? We need to take care of the case where n does not equal 3. Because for when n does not equal 3, we still have a differential equation, right? Even though Bn itself is equal to 0, the differential equation when Bn is equal to 0 is just going to be a first order homogeneous differential equation now. So just closely follow along with what I'm writing right now. So this problem earlier was n equals 3. This is the case where n does not equal 3. And this is just equal to 0, right? So going with what I was just saying, right? And this is a first order homogeneous diff EQ now. First order homogeneous diff EQ. And these are a little bit easier to solve because these are problems that we have seen before. This is like things we see in MATH-241 all the time, right? So let's move the a as sub dt is equal to a negative n pi squared a sub n t. And then if we take the integral of both sides and then solve, we should end up with a sub n t is equal to c1 e raised to the negative n pi squared time. So now we have to deal with the coefficient c1 for now, right? So now let's apply the time equals 0. So at time equals 0, a sub n 0. We know that a sub n 0 is going to be equal to two values depending on whether or not n is odd or even. So this tells us that c1 is equal to either. So let's just quickly copy and paste the relation above. So c1 is either equal to 8 over pi n or 0 depending on whether or not n is odd or even. Let's box this as well because this is important. Right, so therefore we know the value for c1. We know that our arbitrary coefficient here. So these two values will combine together now. Okay, so this has been a very long and garbled process. So, okay, so now let's try to sum everything up into what I'm trying to say here. So a sub n of t. So the reason why we were doing all of this, right? A sub n of t has two different values depending on whether or not n is equal to 3 or n is not equal to 3. Right? So for when n is equal to 3, we have a very special relationship for a sub n of t. Sorry, for a sub 3t. We have this relationship right here. So for when n is equal to 3. This is going to be equal to a sub 3t. So for the very special case of n equals 3. However, when n does not equal 3, we have a dependence on odd n, or even n. So our general solution for a sub n of t can be found here. Where c1 has two values. So for odd n, c1 is equal to 8 over pi n. But for even n, c1 is equal to 0. Right, so this basically sums up like what we were doing throughout this problem. Okay, now we have to write the final solution, and the final solution sucks. So sad face. So the final solution here for this problem, so throughout all this stuff that we're doing, right? So remember that our original claim was that u of xt was an expansion of n equals 1 to infinity of a sub n of t times sine n pi x. So now we know the two potential values for a sub n of t, right? So a sub n of t has a very different value for n equals 3, but it also depends on whether or not n is odd or even. So the final solution for this problem, right, would be u of xt. So we need to explicitly isolate the n equals 3 term. So to do this, I'm just going to take this here. So this is for n equals 3. So this will be evaluated explicitly as sine 3 pi x. So this term right here, I'm going to quickly annotate, is for n equals 3. Plus an infinite summation starting from n equals 1 to infinity. But we're going to explicitly state for only odd n, excluding n does not equal 3, right? So the summation is only from n equals 1, 5, 7, blah, 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 right? And this includes the coefficient 8 pi n, so that's the coefficient for all odd n's, whereas the other ones are just equal to 0, e raised to n pi squared t times the eigenfunction sine n pi x. And this would be your final solution to this problem. Okay, so just to reiterate myself on what I've said earlier, the non-homogeneity of the problem is now inside the coefficient a sub n of t, right? So notice how these coefficients for a sub n of t are clearly not constants, right? And that's a direct consequence of the fact that the non-homogeneity of the problem afflicts the solution in some form. And let's quickly overview what we just did, just to make sure that it's clear and makes somewhat sense, because this is a very annoying process. So the first thing that we did was that we identified that this was a non-homogeneous problem, non-homogeneous PDE with homogeneous boundary conditions, and the way to solve this is using eigenfunction expansion. So the first thing we did was we defined an expansion, right? So we defined an expansion u x of t is equal to, we basically guessed the solution, is I guess the correct phrasing, right? Where a sub n of t contains the non-homogeneity of the problem, whereas phi sub n of x contains the homogeneous solution to the problem, and we're trying to essentially expand the solution in terms of a Fourier series where a sub n of t is a non-homogeneous coefficient. So then we solved the related homogeneous problem in x and found that phi sub n of x is equal to c1 sine n pi x. And then the next thing we did was that we solved for a sub n of 0 at time equals 0. And this was to essentially solve for the coefficients down the road. And we found that a sub n of 0 is equal to 8 over pi n for odd n, and for even n, it's equal to 0. Then we more generally solve for a sub n of t. And the way to do this was by plugging into the original PDE, and then solving that PDE in terms of a Fourier series for b sub n, where b sub n was this differential equation in terms of a sub n of t. So there's a lot of like subsets of subsets here, but hopefully my logic and like handwriting makes sense to what I'm trying to convey. And we found that in solving the Fourier series for b of n, when n is equal to 3, b3 is equal to e raised to negative pi squared t, but for when n is not equal to 3, b sub n is equal to 0. The next thing we did was that we solved the differential equations for these two different cases. So for when n is equal to 3, we have a differential equation, a first-order non-homogeneous differential equation that after solving gives us a messy coefficient for a sub 3 of t. Afterwards, we solve for the remaining coefficient for when n does not equal 3, and then in solving that, we get a sort of relationship that looks like the standard like time equation that we've seen before, but has a dependence on odd and even n. Finally, we put everything back together. So we notice that for when n is equal to 3, we have this very explicit relationship that's not covered in the n does not equal to 3 general case, but for when n does not equal 3, we have a general solution where c1 varies depending on the n. And then putting everything back together into the final solution, for the n equals 3 case, we have to explicitly separate it out from the rest of the solution because it differs so wildly. But for the other problems, for when n does not equal 3, we're able to put into a summation for only odd n's. And yeah, that's basically eigenfunction expansion. These type of problems will definitely take practice. They're not easy. They're not going to immediately come by to you, but they have come up so frequently in past finals and I think it's like of paramount importance for us to be able to figure out and understand how to work out and do these problems essentially. So I hope this video has helped you out. Please let me know if you guys have any questions. As usual, please feel free to shoot me an email, piazza, yada yada yada. So yeah, hopefully this helped. And yeah, good luck with your studies.